Our third speaker is Professor Alexei, visiting professor at the Department of Mathematics at Imperial College London, a specialist in quantum computing and secure machine learning applications. With over 20 years of quantitative finance experience, he was named Quant of the Year 2019 by Risk magazine for his research on the application of machine learning techniques to risk factor analysis and portfolio optimization. In his presentation today, Data Anonymization on a Quantum Computer Density Matrix Classifier, Professor Alexei will showcase a novel approach to data anonymization using quantum feature maps and its applications in sensitive domains such as medicine and finance. Please join me in welcoming Professor Alexei.
Okay. Thank you very much for very kind introduction. And please let me know when I have 5 minutes left. I have too many slides, so I have to stop at some point. It's a great pleasure to present today at ADIA Lab Symposium. I spent 3 years at ADIA. I enjoyed Abu Dhabi very much. And then I spent another year at ADIA Lab. So it's great to be back in Abu Dhabi and see so many familiar places. Also, exactly last year, I enjoyed hospitality of University of Salamanca, where I also presented on quantum computing. So it's great again to see old friends. And today I will be talking about data anonymization on a quantum computer, which is a topic that relates to many talks we already heard at our symposium. We'll be talking about quantum computing, quantum machine learning, data privacy, importance of performing machine learning, preserving data privacy. So without further ado, let's go into the history of quantum computing. Very often, the idea, the concept of quantum computation is attributed to Richard Feynman, a famous physicist. However, even before Feynman formulated a kind of exact definition and concept of quantum computation, such physicists and computer scientists as Charles Bennett and Paul Binev already did a lot of work in the field of quantum information theory. And at the time, it was clear that computation is basically quantum computation, and classical digital computation that we're all familiar with is just a special case. Feynman's PhD advisor, John Wheeler, actually is known for coining the phrase "it from bit," meaning that the most fundamental element in our universe is actually information. It means that we can actually derive the laws of physics from just a few postulates of quantum information theory. So that was in 1980s, and this idea was developed further by many researchers. And in 1990s, we already had the first generation of quantum algorithms. You probably heard about Peter Shor's algorithm that should at some point undermine RSA encryption and undermine our internet security. It's an algorithm that provides exponential speedup, and every time we have exponential speedup, it's a big deal. It's very important. It's not the only algorithm with exponential speedup. We also have Deutsch-Jozsa algorithm. However, these quantum algorithms require large-scale, fault-tolerant quantum computers, which we still don't have. What we have now are small, fragile, experimental devices, definitely working quantum computers, but we are not there yet, so we cannot actually run Shor's algorithm and undermine Bitcoin. But what we have now, so 40 years after the idea of quantum computing was born, what we have now is an era of noisy intermediate scale quantum computers. There are multiple companies building quantum computing devices using various modalities: superconducting qubits, trapped ions, neutral atoms, photonics, you name it. And we discovered that existing quantum machines, existing quantum computers, actually can do something productive. We can already put them into good use if we find the right algorithms, the right models. And it turns out that what is right for these computers is quantum machine learning applications. Because these models, these algorithms, they don't require large computers. We can actually run them on small computers. And to some degree, they are noise tolerant. So on this page, I have John Martinez and Chris Monroe. John Martinez designed a quantum computer for Google. Chris Monroe is founder of IonQ. And it's actually a great pleasure to mention John Martinez because he received the Nobel Prize in Physics this year. But last year, he participated at our conference, the first quantum computing conference in Abu Dhabi. So we were welcoming John at Quantum Computing in Finance, organized by Idea Lab. So Idea Lab definitely has links with many Nobel Prize winners in physics. Again, we have the pleasure of welcoming 2 Nobel Prize winners in physics at this conference, and John Martinez attended our conference last year. I want to say that quantum computers are inevitable. It's not that we want or we don't want to build them. They're going to be built. We have to build them. One reason is that we have a huge demand for compute power, which we can satisfy. So here we have a price chart of NVIDIA, which is the most valuable company in the world. Well, it became the most valuable company in the world earlier this year. I don't know what's the current share price of NVIDIA, but I believe it continues to go up. Why? Because AI, ML, consumes any amount of compute power we can produce. Regardless how much we have, we want more. Until now, we satisfied this demand, at least partially, due to famous Moore's law that says that the number of transistors in integrated circuit doubles roughly every 2 years. And therefore, with this huge exponential growth in technology improvements, we can actually build more and more powerful classical computers. But there is a natural limit to how many transistors we can put in a single integrated circuit, mainly because the size is already so small. You can see that this year we are going to reach 2 nanometers, that any further improvement will take us to the limit of what is possible in classical physics. So once we get under 1 nanometer, we have essentially something that already would have quantum mechanical effects. Effective radius of a silicon atom is 0.2 nanometers, so anything below 1 nanometer means that we have to deal with quantum mechanical effects. That would clearly undermine any classical computation. So I have 2 pages which are slightly technical. So please forgive me for having some mathematical expressions here. But these pages are important. So this page shows the difference between classical machine learning and quantum machine learning. So classically, a typical machine learning application, typical machine learning model would have input, which is a vector of features. Then we would perform a classical feature map. For example, we would take this input vector of features and would expand it into a high dimensional derived vector. So we would have projection into a high dimensional space where classification can be more easily done. And then we would perform classification. So the output is a class label. And the key element here is a kernel function, which is a similarity function. We need to be able to understand whether two samples are in some sense close to each other or very different. So that's what the kernel function does. And classically, we usually work with a Gaussian kernel, which is very powerful kernel function or similarity function. In quantum case, we again start with the same vector of features, only we perform quantum feature map instead of classical feature map. And quantum feature map is performed on a quantum computer. We have to run quantum circuit. So the end result is again a vector of derived features that lives in a very high dimensional space. Traditionally, we use Dirac's notations, bra and cat notations for such vectors, mainly indicating that we are working with complex numbers. Because in classical machine learning, we work with real numbers. In quantum case, we work with complex probability amplitudes. But superficially, expression is very similar. We end up with a derived vector in a high dimensional space where we perform classification. And again, we need to specify a kernel function, the measure of similarity. And in quantum mechanical case, we have a choice between is a simple inner product of two vectors or a function called fidelity, which actually widely used in physics and measures how similar or dissimilar are two quantum states. Right. So with one sample, it's clear. We perform quantum feature map. We transform classical vector features into a quantum state that lives in a high-dimensional Hilbert space. What if we have a large data set? Okay, then we perform quantum feature map for every single sample in the data set. And then we perform the next step, which is we calculate the outer product of two vectors. And if we then combine all the samples together, all these outer products of these vectors together, we end up with an object which is in physics called density matrix. So the whole data set can be encoded in an object called density matrix. And then if we have several data sets or several classes, then we can calculate the distance between data sets, the distance between classes by calculating this very simple function which measures a distance between two density matrices. So that's the whole idea. Actually, these two steps can be done classically if we have sufficient memory. The difference between quantum computing and classical computing, or the main benefit of quantum computation is that we can actually operate on systems that classically would require enormous amount of classical memory. Quantum computers generally are not faster. Classical computers are generally faster than quantum computers. But in classical computation, we can run out of memory very quickly. If you want to store all the probability amplitudes, and the number of probability amplitudes grows as 2 to the power n exponentially. But in a quantum case, we store information in a quantum state, so we don't bother about actually recording everything into classical memory. So we can process a lot of information that classically would simply be impossible because of restrictions on memory. This approach actually leads to many practical use cases. So we have several publications. ID Lab collaborated with Rigetti Computing, and our collaboration resulted in a paper in Risk Magazine on quantum to sample test for investment strategies. Also last year we published a paper in Wilmot on density matrix classifier, so this hybrid classical quantum systems that performs classification. We also applied the core methodology to cryptographic use case where we performed symmetric encryption on a quantum computer. If you're interested in more use cases and more applications, more models in QML space, then we have a second edition of our book on QML applications in finance. And now we arrived at the topic of today's talk, data anonymization with density matrix classifier. It's a new paper. It was published only a month ago on Cryptology Print Archive. And the main idea here is the following. If we have a situation when we work with highly sensitive data that cannot be easily shared, usually is in financial context or medical context. So we can imagine several health providers that would ideally want to share their data to perform classification on a larger data set to train a better ML model. But they're prevented from actually pulling together their data sets because of privacy concerns. We can offer a solution. So rather than these healthcare providers, say hospitals, use a traditional approach to data anonymization which can actually either distort data or remove a lot of useful information from the data, they can do it in two steps. So first, they can transform data using quantum feature map, and then they can encrypt this data on a quantum computer. Once processed in this way, data can still be used to train machine learning models. So data is still useful, but definitely totally anonymized. So how it works? We have example of publicly available data sets. It's a famous Wisconsin breast cancer data set, widely used in machine learning community for all kinds of tests. It has 9 features. And these 9 features can be transformed into a vector, into a quantum state of our system using quantum feature map by running such a quantum circuit. So you can see here that we have 9 quantum registers. On these quantum registers we have quantum logic gates performing transformation of the quantum state. Initial quantum state is initialized as all zero state, and then every layer encodes classical features. This our starting input vector features into the final quantum state, psi of x. So if initial unprocessed, not encoded data looks like this, so we have 9 features and we have several samples from this data set. Then after encoding these features into a quantum state, after performing quantum feature map, we can perform the next operation, which is we would after running a quantum circuit, everything we can do measurement, and by performing measurement many times, we can calculate expectation values of what we measure on every quantum register in various bases. So since we have 9 features and we use 9 quantum registers and we can measure in 3 bases, x, y, and z, we would end up with 27 expectation values of Pauli operators x, y, and z. So every sample is now totally encoded, and most importantly, what we perform is known as a one-way function. Given this encoded sample, it would be impossible to reconstruct the original input for several reasons. So there are several layers of complexity that prevents us to ever guess what the initial uncoded, unencrypted input was. And then, obviously, we can share these encrypted data sets. We can pull them together into a single unified data set and perform standard classical or quantum machine learning operation on fully encoded data. So here we have an example what would happen if you would run either random forest or a multi-layer perceptron or support vector machine or logistic regression classifiers first on each individual data set, or runs them on combined encrypted data set. And we see that obviously if you perform classification on pooled resources on a combined data set, then we have much higher performance. We can extract much higher F1 score in this case. But both classical classifiers working on individual smaller data sets and then combined data set perform slightly worse than the density matrix classifier, the quantum classifier that runs on encrypted data set. So these experiments were conducted on the latest quantum processor, Anka-3 from Rigetti. You can see these points indicate results obtained using density matrix classifier, the quantum algorithm. We had several versions of this algorithm. One performed directly on a quantum computer, on quantum processor, and also we have results from a quantum simulator, which is kind of ideal noiseless quantum computer for benchmarking purposes. And we see that in all cases results are at least as good as on a classical computer working on a combined data set. I think I'm out of time, so I have to stop here. There are another something like 20 pages of this presentation. So I'm very happy to talk to anyone interested in this topic after today's session and share our results and our ideas. So thank you very much.
Thank you, Professor Alexei. We'll open the floor for one question. Or we can move the discussion after the breakout session. Let's thank again Professor Alexei.
Thank you.